This is the 6th video devoted to Bessey shuffle diagrams. And let's just take a quick review of a few definitions. A shuffle S is said to be a Bessey shuffle if and only if S preserves or inverts Bessey sequences. Recall the Bessey sequences of order 8 are 1 0 0 1 0 1 1 0 and its inversion 0 1 1 0 1 0 0 1. Also recall that the position values of the cards we will look at have been color-coded as follows. Positions 1, 4, 6, 7 have been color-coded black, and positions 2, 3, 5, 8 have been color-coded red. And in what follows, one of two outcomes will occur. Either the cards that originally began in positions 1, 4, 6, 7 will remain in those positions, as well as cards in positions 2, 3, 5, 8 will remain within those positions. If such an outcome occurs, we describe it as indicated here. And that's in contrast to something we call an inversion of the sequence. So what happens here is cards that were originally in positions 1, 4, 6, 7 get moved to somewhere among the position values 2, 3, 5, 8. And vice versa. Cards that began in these positions get moved somewhere to these positions here in the set A. And if that occurs, we say inversion has occurred, and it's denoted as indicated here. Finally, before we move into demonstrating the new shuffles for today, recall the Bessey sequences 1 0 0 1 0 1 1 0 and its inversion 0 1 1 0 1 0 0 1 can be described in the following two ways. In the case of the Bessey sequence up above, we see that the ones are in positions 1, 4, 6, 7, and the zeros are in positions 2, 3, 5, 8. For the inversion of this Bessey sequence, namely this one down below, the role of the zeros and ones switch places. The ones are now in positions 2, 3, 5, 8, and the zeros are in positions 1, 4, 6, 7. Our first Bessey shuffle for today is called a Pairwise Transpose. Now that's a name I've given this shuffle. I'm not aware of any name for this shuffle. So as always, we begin with our ordered packet 1 through 8, and we perform the shuffle. Then we look at the resulting new ordering of the packet. From there, we will write the outcome in terms of Cauchy's two-line notation for a permutation, and then convert that to cycle notation, which is one-line notation. So let's go ahead and show you the pairwise transpose. Okay, so how this works, maybe let me take a moment and explain the reason for the name and how there are different ways to accomplish this precise shuffle. Okay, so a transpose is where if you have two things, if you change their positions or orders, that's called a transposition. A pairwise transpose is where you take the top two cards and then you switch them like this. And then you take the next two cards and switch them like this. And then you take the next two and switch their order. And then you take the next two and switch their order. That is actually a pairwise transpose. Now, as we'll see, there are perhaps easier ways of accomplishing that same permutation. And I'll show you in just a moment how to do that. But now that we've done the pairwise transpose, let's go ahead and take a look at the new ordering of the cards so that we can write out the permutation for this shuffle. So as you can see, the new ordering is 2, 1, 4, 3, 6, 5, 8, 7. So in Cauchy's two-line notation, we get the following. The top row is always 1 through 8, and then we get 2, 1, 4, 3, 6, 5, 8, 7. Converting that to cycle notation, we find the following. That 1 goes to 2, so I have an arrow from 1 to 2. 2 cycles back around to 1. So we get a completion of that cycle. It's called a 2-cycle, which is also referred to as a transposition, which is interesting if you think about the name of the shuffle. So we have a transposition there. Now what happens with 3? 3 goes to 4. So I have an arrow from 3 to 4. And then 4 goes to 3. So it wraps around, completing a second 2-cycle, or a second transposition. What about 5? 5 goes to 6, and then 6 returns back to 5. So we get a third transposition. And finally, 7 is sent to 8, and 8 goes to 7, so it wraps back around. So we get our fourth 2-cycle, or our fourth transposition. Color-coded, the cycle notation for our permutation is as follows. Remember, positions 1, 4, 6, 7 are color-coded black, and positions 2, 3, 5, 8 are color-coded red. So we see that black 1 goes to red 2, which wraps around to black 1. Red 3 goes to black 4, which gets sent back to red 3. Red 5 goes to black 6, which goes back to red 5. Black 7 goes to red 8, which gets sent back to black 7. So we can see that something very important has happened here. Each value gets sent to a value of the opposite color. And as we know from our previous videos, this means an inversion has occurred, which simply means that the cards in positions 1, 4, 6, 7 get moved somewhere to positions 2, 3, 5, 8, and vice versa. So we have this situation resulting. Since inversion occurs, we can illustrate that by using our Bessey sequence 1001, 0110 to show that the pairwise transpose, when performed on this packet of 8 cards, will invert this sequence. So let's go ahead and perform the pairwise transpose in the way that I would normally perform it. The first time I showed you, I did it in hand, which can be a little awkward. So the pairwise transpose that I actually showed you just a moment ago can be accomplished as follows. You deal out one card into one pile and then a second card into that first pile. So you do 1, 2, 1, 2, 1, 2. And now we're going to stack 1 on top of 2. Those 4 cards get stacked on top of 3, and those 6 cards get stacked on top of pile 4. And that's equivalent to what we just did a moment ago, where we did it in hand. Now what will occur, the Bessey sequence we began with, which was 1, 0, 0, 1, 0, 1, 1, 0, will now be inverted to 0, 1, 1, 0, 1, 0, 0, 1. So indeed, this shuffle inverts Bessey sequences. And because of that, we say that the pairwise transpose, with stacking as indicated here, is a Bessey shuffle, and that's because it preserves, or in this case, inverts Bessey sequences. Let's go ahead and take a look at the graph. It's on the top row, far left. And this is a graph we have not seen before, nor will we see it in subsequent shuffle diagrams. So here is the cycle notation of our permutation. We've indicated that inversion has occurred. And so what we get is we just get double arrows between pairs of values. So between 1 and 2, there's a double arrow. Between 3 and 4, there's a double arrow. Between 5 and 6, a doubled arrow, and between 7 and 8, a doubled arrow. So cards will just switch back and forth within each of these pairs each time this shuffle is performed. Consequently, this shuffle has order 2. If you perform it twice, it resets the packet to its original order. Now, at the end of this video, I will show you an application that involves all 4 of the shuffles that we are talking about today. But before we do that, let's go on to our second shuffle.